So as I said, the SIMD register is very fast. So that is why we need to take advantage of this single instruction mountable data to get performance. So let's talk about more about SIMD parallelization. So SIMD stands for single instruction mountable data, and it provides the so-called parallelism at the instruction level. So this is not multi-threading. Yeah? Multi-threading is done this morning. It's not multi-threading. Even you have only one thread, you can still use SIMD. And this single instruction can operate on multiple data elements. Like what you can see here, you have one CPU core with, let's say, the index of the CPU core is 0, and you have one single thread, of course, but you can still do the calculation for multiple data within one single instruction. So for SIMD, there are some key points. The first one is SIMD is not multi-threading. And the second one is for SIMD, it uses some special vector register, like what you have seen before, the so-called SIMD register. And for the SIMD registers, it has the SIMD width, and this SIMD width determined the so-called vector length. And then for the SIMD instructions, many of you may think, okay, SIMD instruction is only for computation, but actually SIMD instruction is also available for load and store. So that not only for arithmetic calculation like add, multiply, or fused add, multiply, but also for load and store, you can take advantage of SIMD instructions. And last but not least, if those SIMD instructions are slow, slower than the scalar instructions, and then there's no huge benefit, right? Because SIMD instruction is slow. But actually, SIMD instructions, they are as fast as scalar instructions. So that is why with SIMD instructions, in some cases, you can really get a perfect speed up for your calculation. Okay, let's move slightly to OpenMP again. So OpenMP is, let's say, really powerful. Unlike traditional thinking, OpenMP only for multi-threading. OpenMP is supports SIMD vectorization introduced in OpenMP 4.0. Yeah, and for this for loop, like this vector add for loop, to use SIMD, you can simply put OpenMP SIMD there. Yeah, that's it. Very simple. Yeah, it's very simple to use. And then this loop is vectorized. So compare with respect to the so-called scalar instruction. For example, if you want to add 8, let's say, single precision floating point numbers, if you are using scalar instructions, you need to loop the instruction 8 times. Yeah, this includes 8 scalar add instructions as well as the loop overhead, because you need to do the loop, right? But for the SIMD instruction, there's no loop anymore. If you want to do the add operation for those 8 elements, only one instruction, that's enough. That is why sometimes, in some report or so on, you may see some expected SIMD vectorization may provide even better result than the scalar result, because for the SIMD, there's no loop overhead or minimal loop overhead. But for this one, the loop overhead is high, because here you need 8 loops, right? Every loop is a scalar add. And the possible, you may ask me, how about the so-called vector width of the SIMD vectorization? So this depends on the software, for example, which kinds of calculation you would like to run, and also depends on the CPU architecture. Yeah, for the good news for the new HPC system for HPC2 autos, it has the let's say the widest SIMD vector length, which is 512 bit. So let's say take this vector add example, and from the beginning, it was in the early days, 128-bit SIMD vector was very common. And this 128-bit SIMD vector means with one single instruction, you are able to process, let's say, 4 single precision. SP means single precision floating point numbers. Yeah, that was the history. Now, the very common, let's say, CPU architecture is this AVX or AVX2. This is the most common, let's say, CPU feature available, for example, in my laptop, and I think also in your laptop. Yeah, for Mac, I don't know. But I think Mac also has this vectorization feature. But this 256-bit vector width is, let's say, the very common one, which enables to execute 8 single precision floating point number operations. Operation means load, store, or add, or fused add, or multiply within one instruction. Okay, for the HPC, for HPC, the performance is a key factor, and the vector width becomes even wider, 512, which corresponds to 16 single precision floating point numbers. So this is really a huge benefit for using vectorization. This means without vectorization, your CPU code will be about 1 order of magnitude slower because of this 16. Yeah, this is something. Yeah, this is something. Think about it. Without a vectorization, you will lose this 16 times benefit, and then 1 order of magnitude reduce for the performance is possible. And here is a very brief overview about the AVX 512 instructions. So AVX 512 is a very, let's say, general term. To be more precise, it has more collection of instructions. For example, the AVX 512F for fundamental instructions, AVX 512 BW for bytes and words, and so on. So it's a collection of many instructions. And for this, you will have 32 SIMD registers. So this means you will have 32 AVX512 registers. And for those registers, they have a name of ZMM. For the first one, the name is ZMM 0, and then until ZMM 31. So in total, you will have 32 ZMM SIMD registers. So in order to have the best performance, you need to think about how to utilize those 32 vectors. Yeah, I have a concrete example to show you how to do that, and this really gives you some huge difference in the performance. And last but not least, there are also the so-called op mask registers. So what's the meaning of the op mask registers? So those are the operation mask. Op mask means operation mask registers, 8 registers. The role for those 8 registers is to make some conditional branch possibly done with SIMD vectorization, right? If you have a branch, let's say you want to do some calculation for the first element of your vector, but you do not want to do some operation for the second element of your vector, but you still want to do some operation for the third element or the fourth element and so on. So this is a nasty branch, right? This is horrible. But with those mask registers, this is possible to do it in vectorization, and then you will have no branching, those branching issue. How to do that? Very simple. You just use those mask registers as turn on and off, and then to trigger some special vector registers, and then you will able to do that. I will also have an example for you to show you how it works. But anyway, it's available at PC2. Yeah, this is the key I would like to highlight, especially in the next few years. It's available on autos so that you can take advantage of this fantastic AVX 512 feature